All right, so for on all of our transformations, we did them all but one. One is called dilation. And so let me just read what the textbook says. It says the missions that placed 12 astronauts on the moon were controlled at the Johnson Space Center in Houston. The toy models at the right were scaled down replicas of the Saturn V rocket that powered the moon flights. Each replica is a transformation called the dilation. Well, now, first of all, is this how big the actual rocket is? No. No, it's not how big the actual rocket is. So what do we know about dilations that's different than all the other transformations? Yeah, it's no longer congruent. It changes the shape. Well, it doesn't change the shape as much as it does the size. Okay? So, yeah, because the rocket's still shaped like a rocket. It's just larger or smaller depending on the type of dilation. So, every dilation has a fixed point called the center of dilation. So, this is the center of dilation. In other words, if we were to zoom in on the scale, it should shrink to a point. Okay? And so, which is located where the lines connecting the corresponding parts of the figures intersect. So, for example, if I have two triangles, RST and then R prime, S prime, T prime, if I draw a line from R prime to R, S prime to S, T prime to T, they're going to converge on a point C, which we consider the center of dilation. Okay, so just by drawing a line from the primes to the originals, that's what we get. So with that being said, though, let's go ahead and crank through this a little bit, okay? So it says use a ruler, and for time's sake, I'm just going to write this down, but I put the rulers away, but we could get them out. But for time's sake, because you guys will say stuff like, is it 1.2? Is it 2.5? I'm going to show you something. I'm going to write it down. Now, what's important is not necessarily how you measure it, but there's a relationship between the measurements, okay? So just keep that in mind, and I'll show you. I'm going to teach it to you. So don't get in your feels about, Mr. Adams won't let us measure. No, that's not it. So from C to R prime is 5 centimeters. In other words, if I were to measure from here to here in your textbook, it would be 5 centimeters. Actually, no. From C to R prime is 5 centimeters. Keep in mind, Mr. Adams is really zoomed in on this whole thing. So let me redo this. So C from here to here, this whole thing, if you were to measure that in your textbook, is about 5 centimeters. And then if you were to measure from here to here, that is 2.5 centimeters. So this would be 2.5 centimeters. Okay, does that make sense? And so now if I take the ratio of those two, I'm going to say 5 divided by 2.5. What does that reduce down to? 2. So now if I measure C to S prime, that would be 4 centimeters. And then CS would be 2 centimeters. So C prime, or CS prime, which is 4, over CS, which is 2, what does that reduce down to? 2 centimeters. Right? And actually, I shouldn't be writing down centimeters. This is just 2. Notice that I did it right the first time, because the centimeters will cancel out when you do the math on this. So now from C to T, it's actually 6 centimeters if you were to measure that with a ruler. And then CT, take a guess. What do you think this would be?
6 centimeters.
Well, this is 6 centimeters, but this would be 3. Why did you guys say that? Because 6 divided by 3 equals what? 2. So when we compare all the ratios, what did you notice? Yes.
They're all either 2 times smaller or 2 times bigger.
Yeah.
Depending on which one you go from.
Yeah. So I'm going to Absolutely correct. I'm going to make it a little more formal. I'm going to make it a little more fancy math talk. The ratios all equal 2. Okay? So now what they want us to do is measure and record the side lengths of the triangles. So if I do that, R prime S prime would be 2 centimeters. Take a guess what you think RS would be. 1 centimeter. That's no accident. Now, what about R prime S prime over this? It would be 2 over 1, which is 2. No accident. This would be 2 centimeters. Take a guess what this would be. 1 centimeter. And so this will be 2 over 1, which reduces to 2. This is actually 2.8 centimeters if you're to measure that out. What do you think RT is? That's exactly what it would be, 1.4. So that's why Mr. Adams didn't really make a big fuss about getting out a ruler and measuring it. We should be able to. I didn't want it to distract you from the fact that we have a ratio that is equal to 2. And the corresponding side lengths have a similar ratio up. Notice I use that word, similar. That's going to come up a lot. To 2. So write a conjecture about the ratios in the table. They also equal 2. Okay. Now, what about the corresponding angles? Do you think those are going to double? Well, hold on. Let's look at it. Do you think those angles doubled?
No, they stayed the same.
Do you guys know it? Yeah. They stayed the same. Do you know what I mean by that? If you look at the angle for R, isn't that look a little, they look like they're the same, right?
Yeah.
And angle S looks the same as S prime. So they're the same. They're congruent. So they're the same. The angles don't change. So let's say, I'm going to write it this way. The corresponding, this is a little bit more fancy math way to say this. The corresponding, you guys should be writing this down, angles are what? Congruent. Very good. Okay? All right, so now the explore activity, it says 2 figures have the same shape but different sizes are called similar. Are triangles RST and R prime S prime T prime similar? What do you guys think? You think those are similar? Yes. By the way, I just yawned. It's all in the video. Their corresponding sides are proportional. Their corresponding are proportional. Angles are congruent. Now, I know that's not grammatically correct, but I'm running out of space. You should say something, and their corresponding angles are congruent. It says compare the orientation of a figure with the orientation of its dilation. Well, actually, they have the same orientation. And I'm going to zoom out in a second, and we'll look at both the rockets and the triangles. So they have the same orientation. And so if you don't remember what orientation is, look at this. Whoops. Dang it. Wrong thing. All right. So what they mean is the rocket, the tip of the rocket is pointing up, the tip of the rocket is pointing up, they're not twisted, they're not turned, they're not reflected. Same with the triangle. R is pointing up, T is pointing to the right, and S is pointing to the left, if you want to think of it in those terms. So the orientation, they're not twisted at all. They're not reflected either. It's the exact same orientation, it's just one is bigger than the other. Okay? And if you converge, it's going to have a center of dilation. Okay? Are there any questions on that? All right, so what I'd like for you guys to do now is try to do explore activity number 2 on your own, and we'll go over that in just a second. So get started on the explore activity number